So it's my great pleasure to introduce Jonathan Cohen. Of all the things I was supposed to do to prepare for this meeting, I should have created an introduction. So I'm going to let him introduce himself. He has a long history of research in cognitive architectures from different perspectives, often from the connectionist viewpoint. I heard him give a talk and I said, wow, it would be really great to have that perspective for the people in our community to hear. And so take it away, Jonathan.
Thanks, John. Yeah, I'm actually, thank you for letting me introduce myself. It both spares me the embarrassment and lets me say the things that really matter. The first of which is that I am incredibly honored and touched to be here. As John said, I've spent most of my career building what, I'm not sure I would fancy as cognitive architectures in the sense that you guys mean. I've always admired that effort and aspired to it, but only recently felt like I have anything close to something to say about that. So that's aspirational for me mostly. I'll also say a little bit about history. I actually originally started my career with medical training. I won't tell you the whole story about that. But what I will say, and then went on to get training as a psychiatrist, and basically what I learned in psychiatry is that we're like car mechanics that don't know about combustion, and so beat a path back to basic science. Maybe the best summary of my experience in my medical training was that I often say the best book I read in residency was the C programming language by Kernahan and Ritchie. I got bit by the bug. I started reading everything I could about computing. It seemed like a really good way to think about the brain. Some of you may know Terry Winograd or know of Terry Winograd. I had the fortune of being at Stanford at this time and somehow found my way to his doorstep. And he was very, very welcoming. I said, I want to understand how the brain works and I want to understand from a computational perspective. He says, yeah, boy, we all do. And someday, but we're going to start simple. And he basically set me off in other directions, given that CS wasn't just quite at the point at that time. I was incredibly fortunate, though, not long after that, to stumble into a talk at Berkeley that somebody had told me to go. People were basically trying to get me out of their hair, and so they were sending me anywhere they could to get rid of me. And somebody sent me up to Berkeley to hear about some guy that actually was, I think it was Gordon Bauer who told me about this. And he said there was a guy giving a talk up at Berkeley. His name is Dave Rumblefart. And you might want to go and listen to what he's spewing because it sounds like the kind of thing you're interested in, though, we're not really sure where it's headed. And so I went and heard Dave Rumblefart give a talk about backprop, and the scale sort of fell from my eyes about at least how I could come at it from a neural perspective, but ask questions about cognition. I beat a path from there to his colleague's doorstep, Jay McClelland, and spent my time retraining as a basic scientist under Jay's tutelage, and arrived in 1986 at a time when the holy wars were in full fury. And I hope somebody has transcribed the bulletin boards of the day because some of those discussions really belong in the historical record. I mean, this was when Herb Simon and Alan Newell were there. Jay had just been hired. Jeff Hinton was still there. And you can just imagine the flames that were, I suspect some of you might have even been party to those discussions. During the day, I was, a dutiful soldier in my camp, but I had it turns out there were only two of us in the grad school. This is the psychology department at the CMU. And it turns out that there were only two of us in the psychology department graduate. We started with three, but one bailed. I don't even remember why. And so we landed with two people in our program, me and a guy named Ken Kadinger, who many of you may know. And so Ken and I were both and he was John Anderson's student. And so he and I sort of were dutiful soldiers in our respective legions during the day, but at night we'd sort of crawl out of our tents and bring our candles to some secret spot and talk about how we could find some kind of middle ground, how we could find some sort of meaning in what it would look like to have an architecture that could do the kinds of things that people do and that SOAR and ACT-R were trying to formalize, but in a way that actually happened in the brain. And as I say, that was an aspiration, and it remained an aspiration for many decades. Always sort of close to my heart, especially since I sort of picked a part of the modeling space and connectionism that was the least occupied and the most problematic, which is how do you get neural networks to do something interesting like planning or problem solving? And I ended up having to reduce that to the simplest possible question, which is how can you implement some form of control in a network? How do you get some sense of, intention or goals? And so I spent a lot of time sort of working that through, and I think, we made some progress. Not that it's ever been sort of viewed that way, nor would I expect it to, but in some sense, we sort of discovered attention and how it could be built in neural networks that I would like to think anticipated, the paper that says attention is all you need. In this paper, I will argue that attention is not all you need. It's something you need, but not all you need. Anyway, so that's sort of the background for me. And I feel like, we're in a remarkable point now, and I don't have to say this to any of you. You just heard talks already, the SOAR perspective, how to integrate reinforcement learning or LLMs. And I think that's just absolutely the way we need to go. The question is, how do we do it? And there's lots of ways, and I'm going to articulate a few, and then offer what I'd like to think is an insight about a point of contact that I think might make a difference. So that's sort of the background and a very high-level statement. Let me just start. Let's see if I can get going here. Yeah. By just a little summary. I know I'm preaching to the choir here, but I think it's worth stating nonetheless. We all, well, most of us respect the miracle of symbolic computing. I mean, how could it not be an amazing thing? It's computationally general. It is, got maximum flexibility. I mean, that's just restating the same point. All these words that everybody's in search of now, interpretability and reliability, sort of come for free. I mean, if anybody thinks the brain doesn't do symbolic computing, I'd like them to explain to me how it is that the brain came up with symbolic computing, right? I mean, it's almost a tautology that the brain is capable of symbolic computing, and in some senses, one expression of the miracle of symbolic computing. On the other hand, I think we all agree that it has its challenges. It's inefficient, at least to program or to configure, especially in hyper-complex domains, exactly the domains where it struggled, such as language and visual processing for a long time. I also don't think I need to make this argument at great length, but again, it's worth noting. There is an equally miraculous development, namely deep learning or connectionism or backprop, really, to be specific. That complements symbolic computing. It's computationally efficient. Some refer to it as automated function approximation, which is just a really fancy way for saying you program it without really knowing how to program it, but you give it an algorithm and a lot of data, and it programs itself. You don't know exactly what the program is, but at least it accomplishes something close to what you want. And yet it is sample inefficient, domain specific, and then, as I intimated a moment ago, it challenges our ability to interpret what it's doing, and as a consequence, we have concerns about its reliability, at least in untested domains. So this is sort of, the standard story. So where are we? Well, it's been like this for 50 years, and I'm not sure we're much past that, sort of. What we'd really like is this, right? We'd like some sort of marriage of these two, some understanding, much as physicists understand that, molecules are stochastic and gases are, you can't say where every molecule is, but we can say something about an ideal gas law. And we understand what the relationship between those is. There's the same thing with Newtonian mechanics and statistical mechanics, et cetera. We like what I think philosophers refer to as reduction principles. How do we go from the symbolic level to the lower, finer scale level of description? And that, that's one way of putting it, but I also think we would like to understand at a mechanistic level, how symbols arise. Like, what are the right approximations, and what are the architectural features that give rise to it in something like a neural network? And so there have been a few approaches, right? One, so the challenges are to integrate flexibility of symbolic processing in traditional architectures with, in effect, the efficiency of function approximation and the configurability of neural networks for achieving that. And so there's sort of two kinds of efforts, as I see it. There are neurosymbolic approaches, and this, by the way, I think excludes the SOAR community, at least from what I've heard about it from John's talks and then the few that I heard this morning. I think that's taking a slightly different approach, which isn't fully articulated here, but I think it falls within the sort of general sort of scope of what I consider to be these two approaches, which is one, you come at it from the symbolic perspective. You say, well, there's this deep learning stuff, right? And obviously it's really good at doing certain things. So can we start with the symbolic primitives and then get it to do the programming for us? That's basically what it comes down to. And you know, in one world, this is referred to as program induction. This is sort of the Tenenbaum camp. You know, we're going to assume that there are these symbolic primitives, and we're going to sort of get the neural network to do the program induction for us, but it's still going to be symbolic processing because we built that in. And I think there's a certain spirit of that in the kinds of architectures that were talked about this morning. You have the SOAR architecture where you specify certain kinds of operations that we can call are symbolic, and then you're going to get deep learning to sort of augment that by doing some of the programming for you. And this stands in contrast to, oh, sorry, this is often referred to as the neurosymbolic approach. I'm not sure exactly whether that's the best term, but that's the one I keep hearing referenced. And so in response to that, I'm going to coin a new term called the neo-connectionist approach. So the traditional connectionist approach is that you start with undifferentiated stuff, all these little processing units that have nothing but weak weights connected between them, and you pick a statistical algorithm that trains them, and you give it lots of data, and it trains itself. Right, but there's never any, it's often referred to as end-to-end training. There's never any pre-specification of any kind of structure, whether it's representational or architectural, other than maybe the feed-forward stack of layers in the network. And I don't know how many of you have ever heard the light bulb joke about connectionists? Anybody heard this? How many connectionists does it take to screw in a light bulb? If you laugh, you'll understand connectionism. None. If you wire it right, you don't need the bulb. So at least some people understand connectionism, or at least the historical connectionist approach. But I will say, this is one of the things I never bought. And I think that was always sort of in, you know, it made my sort of stomach a little queasy, was just to think that it was just going to be a bunch of undifferentiated units and a learning algorithm. There has to be something that evolution learned that makes us different, for example, than apes, right? That have a lot of neurons and are able to learn. And as far as we know, there's really nothing qualitatively different about their brains from ours. There's not a cell type or a particular circuit that anybody's found that makes the ape different from us that we know of. And yet we do something qualitatively different. So there's got to be something. Is it just more neurons? That may be part of it. It seems unlikely. And so when I refer to neo-connectionists, I refer to the following. The selection, as parsimonious as we can be about that, of inductive biases that favor abstraction, effectively that favor the discovery of symbols. And there are two broad forms of inductive bias we can imagine. One is architectural, and that's what I'm going to spend most of my time talking about, but I want to mention the other one as well, which is training. And, you know, we don't learn to do math just by being in the world. Our brains are capable of doing symbolic processing, but they certainly don't exhibit all the features of symbolic processing if they aren't subject to some kind of curriculum. If you don't go to school, you don't learn math. Maybe you pick up a book, but if you don't have some kind of structured introduction, you don't discover math simply by your experience of the statistics of the natural environment. You have to have some sort of shaping of the procedure. And I'm not going to say much about that in my talk. If there's time, I'd be happy to say more about that. We've begun to explore this, and I think we've made a few more discoveries about the kinds of things, at least qualitatively, that help take advantage of and augment the kinds of architectural biases that I am going to talk about. And the second one is exactly that, architectural. Structures to the system that, though they themselves don't ensure that there is symbolic processing, make it possible under the right curricula. So where does this leave us with regard to the state of, of these ideas in the context of LLMs? Well, in some sense, they're sort of, we could debate this, right? But the first approximation, they're doing a pretty good job of faking symbolic processing if they're not doing it per se. At the end of the talk, I'm going to argue that they actually are doing it in the most, formal, rigorous sense of what one might mean by symbolic processing. But for the moment, let's not assume that and just say there's growing evidence of abstract reasoning in large neural networks. This is a paper by one of my colleagues, Taylor Webb, who together with Keith Holyoake went through and tested the then sort of current model GPT-3, this is several years ago, on a bunch of analogical reasoning tasks and various other measures of abstraction like Ravensburg matrices. And I'm not going to go through all the data here, but suffice it to say that GPT-3 was pretty much at human level performance. And as far as we can tell, GPT-4 in many ways exceeds it. It can do analogies that at least undergraduates can't solve. So there's at least prima facie evidence that they're doing something symbolic-like. But, and again, I think you all know this, they're wildly data inefficient and also energy inefficient. I'll say a word about that, not too much, but I'll mention it in just a moment. And they're largely domain specific, right? You train up, ChatGPT to answer any question about history, but it can't drive a car, no less fry an egg or raise a kid. So they're impressive, but they're not truly what we're looking for. And there is an existence proof of what we're looking for. It's ourselves, right? And so this is just a little made up slide to make the point. Again, I suspect I'm preaching to the choir, but I think it's sort of fun to reflect on. This is just a sort of fictitious graph of different tasks. Those are the different sets of bars, and then different agents in the different colored bars trying to perform these tasks. So one is building a web. Well, spiders do that pretty damn well. Building a dam, beavers can do that, build a nest, robins, et cetera, out to chess and go and navigate. And, in that case, we have artificial agents, AlphaGo, AlphaChess, Tesla Autopilot, that do pretty well at, or in some cases, radically exceeding human performance. So if we look around us, we're populated in a world now by agents that pretty much beat us on anything that we might want to take on, right? And yet, if you connect the dots and you ask, well, how well does any agent do all of these things? It's not even close, right? The area under that pink line, which is connecting the human dots, is vastly, orders of magnitude more area than any other connection of any other lines. And that just makes the point about our flexibility. So even if I had to build a web, I wouldn't do it as well as a spider, but I could catch a fly, right? I could get some string and spray some tacky glue on it. And I might get lucky if I put it in my pantry. In fact, I'm sure I get lucky, not flies, but moths. What does this say? Well, it says that there's some kind of sweet spot between flexibility and efficiency. We have a near limitless range of tasks at adequate performance. That's our flexibility. And we do it with reasonable amounts, often little or no training. I think one of my colleagues, Tom Griffiths, estimated that GPT-3 took something like 5,000 years worth of reading, or what the equivalent of a person would have to do if they wanted to get exposed to the same amount of information. And we do it in what, maybe 10 years, so like 3 orders of magnitude less data. And I'm not going to emphasize this point, but it's hard not to mention it. We do it on 20 watts. And I did a quick estimate of what GPT-3 required in energy, both in terms of training and then operating costs, amortizing it over whatever the 3 or 4 years that it was useful until it got replaced. So the training was, I think, something like 10 megawatts, and operating when it was being used was like about 1/10 of a megawatt. So if you sort of average it out, let's call it a megawatt. A megawatt to do a fraction of what we can do on 20 watts. So there is a lot of room for improvement. Some of that may be biological, like literally physical, like, chemistry for better living. But there's got to be a lot of it that's algorithmic. It can't just be the efficiency of chemical computing. So how does it accomplish this? All right, so that gets me to my talk. Here's the outline. I'm going to propose an architectural principle. I'm going to show you that it works in at least a simple toy setting. I'm going to show you how it works in that toy setting. And then I'm going to discuss in much more sort of hand-wavy, broader form, although there are papers that substantiate much of what I'll refer to, its generalizability across different architectures, its relationship to symbolic, in particular production system architectures. I'll be eager to hear what you all think of that, whether I'm doing it justice or not. For those who are interested, I'll say a word about biological plausibility. That's something close to my heart, maybe not everybody's. And then if there's time, though I doubt there will be some variations on the theme that start to get to applications, at least to human cognitive science, where we can use these architectures and start to provide pretty sort of detailed accounts of the space of human cognition, at least in the domain of semantics, where with these architectures, we can start to account for sort of all of the historical semantic idiosyncrasies like the triangle inequality and the reversal similarity effects. And I say that as a tease because I doubt I'll get to it, but we have a couple of papers on this if anybody's interested, and if there's time afterwards, I'll be happy to say more about it. All right, so let's start with the architectural principle. It was inspired by a paper about 10 years ago by some people at DeepMind called the neural Turing machine, about an architecture that they proposed called the neural Turing machine. Anybody here know about this architecture? People familiar with this? I'm surprised on many counts because I think this was one of the deepest insights that DeepMind had. In fact, I think it was probably the only insight that I'm aware of that they put on the table that was a real insight. That was a real innovation. They did amazing work. Don't get me wrong, of course. You know, who am I to say? But it's for sure true in building out neural networks. But most of the ideas were borrowed from others. This one was in many ways original, and it sort of scratched an itch I sort of had for a long time and caught our attention. The innovation was as follows. Let's take the standard LSTM, which is what they used to solve the Atari games, and for the most part was used to solve Go and chess and most of the other things they've done. Variants thereof, LSTMs you usually think of using backprop, but you can do it with the reinforcement top end or loss function. There's a talk this morning, I think Bob Ray talked about stuff sort of like that. DQNs are a version of that. And add to it an external memory. Basically, what we would, as psychologists, call an episodic memory. A system wherein that LSTM, in addition to encoding information into working memory and then sort of using that, integrating that information, and then spitting something out and deciding when to encode stuff into working memory using its gating mechanisms, also decide when it would write essentially to a Turing tape. It would take its memory state or some part of its memory state and simply put it in a cache, RAM, stored veridically, but retrieved in a content addressable way. So when it decided to retrieve something, it would do it through a standard dot product match. And I'll sort of hit one of the punchlines here by saying, essentially the matching procedure that production systems use when they match conditions in the production rule with the state of working memory. This is not working memory, by the way. This is external memory, which is interesting, and I'll come back to that later as well. But in the sense of being able to sort of match to states and then retrieve new states that might affect what's going to happen next, that's going to get brought back into the LSTM. Here's the working memory of this system, if you have to label it, and then decide what to do, would give it the chance to sort of basically implement a Turing general computational device. This is, and that's why they called it the Turing machine. And they went on to show that if you train this thing, and all of this is trainable, and I'll say a word later about how one might train this part of it, but all of this is trainable. And so it starts with sort of no representations here and empty memory, and it just learns representations here. It not only learns what kinds of mappings to do from input to output, but also what information it needs to be able to store in a way that it can later retrieve it, right? And what they showed is that this machine could be trained on genuinely symbolic tasks, things like copy operations, where you give it X, arbitrary number of Ys, and then a signal to say retrieve X, right? And if you're familiar with LSTMs or any kind of recurrent neural network, you'll know that they suffer horribly from gradient loss. And if you try and improve that, then they don't really have their integrative properties. And so there's a sort of Scylla and Charybdis that you have to walk, and they're very hard to tune to accomplish symbolic light computation at the same time that it preserves the properties of sort of standard neural networks of integration and sort of averaging and whatnot. So, okay, so this thing can get around that by storing here. And as I say, they did a pretty good job of showing that at least on some tasks, it achieved what one might argue is symbolic light computation. The problem is, much like its successors, the transformers, and the transformer is a variant of this in certain ways. I won't have time to go into that in any detail, but again, if anybody's interested, I can come back and say this. This is basically, I wouldn't say it's a notational variant of a transformer, but it's a slightly rotated and tweaked and reparameterized transformer, or the other way around. Transformer is a reparameterized version of this. One can think of it. The problem is, like transformers, it's insanely data efficient. It took hundreds and hundreds of thousands of trials just to get it to learn to do a copy operation. So it was sort of a proof of principle, but it didn't achieve this efficiency that at least we know that the human brain is capable of. If I give you a copy operation, that you might take a little bit of exposure to figure out what I mean. But even if I don't tell you exactly what I'm doing, if I go A, B, 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 A, and then A, B, 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 A, and then Q, L, 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 Q, you'll get it, right? At some point, you'll get when I signal tell me what the first thing was, you'll know how to do it. So we looked at this and we realized it's suffering from the same problem that all neural networks suffer, which is that it munges everything together over here. Even though it can cache stuff, the loss is coming through here, and that loss is getting infected by the data much as whatever it stores here, right? And the problem that neural networks suffer, if there's any one thing that, for me, anyway, that they suffer from, it's from the inability to tell when it's useful to abstract and when it's useful to use the data. And this thing doesn't have any advantage over any others. In principle, it could abstract, but it doesn't know how to do it without getting hit over the head with the data, much as transformers. So we thought, well, what if, instead of just thinking about this as a tape, we thought of it as a binding mechanism, which from a neuroscientific perspective, of course, is the way it's always been thought of. This, insofar as you think of this as episodic memory, in neuroscience, we think of this as a model of the hippocampus, which is doing binding. I say this for those who appreciate what I'm referring to. I don't want to take time to slide check on that, though. Again, I'm happy to come back later if people are interested in that. But here's what I mean in the present context. All we have to do, went the wrong direction, is add another LSTM, another controller, if you will, on this side. And the trick is going to be that whenever this thing writes here, this thing will write. And whenever this reads, this will read, and vice versa. And when they write together, those elements will be bound. That's what this orange line means here. So if I write here, it's just like a dictionary in Python, right? If I write a key, I write the value. Here it's labeled as keys and values for the machine learning community, but really you could just call these fields, right? Or entries, and they're getting bound. And I can retrieve either by matching this and then I'd get back this plus this, or I could match this and I would get back this. If I match this, I get this plus this, okay? But critically, this side never sees the data. These are binding only in the sense that when you retrieve this, you retrieve this, but this side never sees this, and this side never sees this. That is, there's a firewall. Critically, by again, the ingenuity of DeepMind folks in developing this, and in so doing, making this differentiable, and I'll show you later how you can do this, you can differentiate through all of this. So I can train a network just on this with the loss coming here, or even the loss coming here. And that's the example I'll show you in a couple of minutes, okay, where the loss comes from here. And it will benefit by the gradient errors, both here and anything that happens here. You can differentiate through this. So you never get the data corrupting this, or these representations corrupting the data, but the errors can pass through. Okay, mathemagic, as John Anderson liked to say. And again, I'll show you how that works in a bit. So what can we do with this? Well, we can train it. And critically, because of the similarity-based retrieval, then basically when this thing is retrieving something based on its similarity to these, this is getting whatever, it's being forced to sort of respect any relationship among these that this might observe between these. Or better still, to put down symbols here that will be useful in responding to that relation. And I'll show you exactly how that works in a minute. So the critical thing is that when you train this, what can this possibly learn? It doesn't know anything about the data, but because of the similarity-based retrieval mechanism, it can only learn relational structure, that is abstractions. It's forced to abstract. It has no choice to abstract. It either learns nothing or it learns abstractions. It never sees the data. Okay? And so this is an inductive bias that we refer to as the relational bottleneck, because in effect, it's a bottleneck. It's not allowing the data through. It's only allowing sort of relation information through. Okay? So first, I just want to show you that it works, and then I'll unpack how it works, and then both sort of operationally and then under the hood in terms of the neural network aspects of it, and then come back up and say a little bit more about how it might apply more generally. I should say, if anybody has any questions or concerns along the way, please jump in and interrupt me. I'm happy to answer questions as I go. Okay, we refer to this, by the way, as the emergent symbols through binding network. And I'll make that clear why we call it that in just a moment. So we trained it up on simple relational tasks. drawn from Raven's progressive matrices. So we simply ask the network to see two arbitrary symbols and say whether they're the same or the different. Here, of course, it would be different. If they were both the same, they'd have to say the same. Relation match the sample. Two things are the same here. Now pick which of this pet set goes with this. It would have to pick this one because these are the same. If these were different, it would have to pick this. Distribution of three, which I'll show you in just a moment. And then abstract sequence rules, which I'll come back to at the end. So we trained it on all these kinds of tasks, and we did it in a space of Unicode characters, where in this case we had 100 different arbitrary characters that had no relationship to each other. The network wasn't trained on these other than to simply embed them arbitrarily. And we trained it to learn to do these tasks first, just to see if it could do the tasks, having given all the stimuli. And then we throttled it back and we trained it only on 85% of the stimuli to see how it generalized to these other held out stimuli. So we played the typical machine learning generalization game. And then we throttled it back to 50%, and we throttled it all the way down to 5%. 5%, which is, I won't explain why 3 is 5% of 100. It has to do with how many you have to show. But the bottom line is we trained it in the limit on just the number of symbols, in this case, just 3 symbols, that were sufficient to perform the task. No more, no less. So just like if I was to say to you, cup, tape, sky, or sorry, cup, tape, cup. And then I go sky, lamp, you say sky, right? I only needed 3 items plus 2 more as exemplars. That's why it's 5% of the 100, okay? So we train it on exactly that number and ask how it does. And here are the results. We did it with, our model is in red, the SVN is red. We did it with a transformer, the neural Turing machine itself, a straight up LSTM. Ironically, a prior candidate from DeepMind called Relational Net, which did the worst. That's the green one, it can't do anything. But all these other models do pretty well up to about 50%. But when you get to radical generalization, they're at chance. And the model is perfect. And not only is it perfect at radical generalization, genuinely extrapolating from like the smallest number of exemplars needed to illustrate the rule, but it does it with insane sample efficiency. Instead of hundreds or thousands of epochs, it's like 10 or 20, depending upon the rule, some are 50, but like orders of magnitude faster than others, okay? So what is the claim? How does it work? Sorry, come back to the claim in a minute. So here's how it works. Here's the distribution of 3 tests. The distribution of 3, you're given 3 items, and then you're given 2 more, and you have to pick what the completion is of the second set. And it's called distribution of 3 because there's a distribution of 3 unique items here. This, in some sense, is the simplest, most basic symbolic processing task. So I have to basically recognize that I have one of these, and one of these, and then I get 2 of these, and I've got to pick the answer, which is, of course, going to be the square, right? That completes the set. So here's how it works. Oh, and I should say, in this particular model, our thumbs were on the scale. We didn't train it to decide when it was going to encode from one side and then retrieve from the other. We had an external controller that synchronized both when these things wrote and when they retrieved. We're now in the process of building models that know how to learn how to do this. And at the end, I'll show you LLMs have figured out how to do this. I mean, we know that now, okay? And I'll show you examples of that in just a moment. But for the moment, just we'll allow that there's a controller that says, okay, this thing needs to look, and also there's no sequential attention in this. The model itself doesn't have it. We're hand sort of sequencing the stimuli. We do have models that know how to do the sequential attention now. So we give it the circle, and it encodes the circle, and then it lays that down in its memory trace. And this thing starts out by just having to write something because it's commanded to write whenever this thing writes. So it writes some arbitrary thing. I'm showing you what it looks like once it's learned, and I'm just picking the letter A to designate sort of what it learned to represent there. Okay, so it represented some thing called A. Could have been anything. Okay, and now it sees the square, right? So it encodes the square and it writes down square, and this thing then decides to write B. And then it sees the triangle, and so it writes the triangle here, and this thing decides to write C. That's what it's learned to do, okay? And so now we've encoded the stimuli, and now we're going to start encoding and retrieving, right? So here we've been writing to memory, and now we're going to retrieve. So it sees the triangle, it encodes the triangle, and it retrieves, it does a match, and triangle matches something that's in memory, right? And so it retrieves triangle. And remember what I said before, when this retrieves, this has to retrieve. So this gets back a C. Okay. And that goes into the LSTM, and it does two things. It encodes that it's seen a C. Remember, LSTMs have the capacity both to serve as a memory and sort of an integrator, and they're really good at learning sequences. So this thing, one of the sequences it's learned, you've already seen, is to write down A, B, C in these slots, right? And then when it sees the C, it learns to encode that in working memory. And then we see it looks at the circle, it retrieves circle on the sort of the data side. That's associated with the encoded A. It retrieves A. So now it says it's seen A. That's in its working memory. And now it knows it's looking for B. It's learned this, right? This is all this stuff over here has been learned. We didn't code any of this. It's just the LSTM learned to do when it was trained on 20 or 30 epochs of this. Okay. So it knows that it's seen A and C, and so it's looking for B. And so it encodes the pentagon. Now we're looking at the options, and so it's going to look at the pentagon, and it's not going to find anything. So it does a question mark, and now it's keeping track of positions. So position 1 doesn't know what's there. Position 2, it goes with square. It retrieves square, retrieves B. It was looking for B and it got B. That's a match to its internal working memory state. Okay, and so now it encodes that it saw B in position 2, rinse and repeat. It's a circle. There is a circle there, but that's in position 3. And now at the end, it knows that it's looking for position for B, and so it reports out whatever is associated in working memory with B. So I know I sort of put this in words. You'll have to trust me that this thing trained as efficiently as it did. What I'll argue, what I'll tell you is that when you analyze the representations here, these are literally symbols in the sense that whether I give it circle, square, or triangle, asterisk, pi sign, plus sign, it doesn't matter. All it has to do is get 3 different things here, and every time it just writes A, B, C, and then it just goes through this routine. And because it only is using symbols here, it's basically binding those symbols to the fillers, the datum, right, as they come in the order. And because it knows about the order of those symbols, it's learned a function, which is the distribution of 3. And it can perform the task perfectly over any data that it can encode here. It doesn't matter what those data are. It never has to have been trained on them past one set to learn this function. So what is this thing learned? Or how can we describe it? It's using external memory, not just as RAM, but as a bottleneck, as a way of arbitrarily binding 2 separate items without one affecting the other, freeing up one of them to learn to be entirely abstract. So it's learning a function over here. It's learning an abstract function, 1, 2, 3, keep them all different, right? And this is serving as the variable binding apparatus that one needs in any sort of self-respecting, Van Neumann architecture. And then together, you get the emergence of symbolic computing. It learns the symbols here. Super simple example, but I think it passes muster in terms of the formal claims that are being made here. Okay. What's really cool is that once you see this, you can start implementing it in a variety of ways. So one of our colleagues at Mila, a guy named Carlo Kurg in Yoshua Bengio's lab, took a look at this. This is the ESBN model. And he said, what's this thing really doing? Well, in the abstract, it's building up over the set of data a correlation matrix, a similarity matrix of each vector with every other vector. And then it's just reading out from that what the data, what the data are, or what the right response is at each trial. And so he simply reconfigured this to be simply a correlation matrix that gets populated by the data, and then a decoder that reads out of the similarity matrix the answer. And this is in effect acting as the relational bottleneck, this correlation matrix. It's not as plausible because he had to construct that similarity matrix, or he had to sort of lay the rows down manually with C code. This is doing it with an LSTM and learning how to do that with this external memory and the LSTM. But in principle, it's doing the same thing. And when you run it, it learns all the same rules. In fact, it's a little cleaner because it doesn't have the gradient loss of the LSTM for learning the function. You can simply articulate the function in the form of this similarity matrix. And so it's a little bit more efficient, but it's the same idea. Okay, and notice that the data never make it past this, right? This thing is only operating over the similarity matrix, which has lost all the data themselves. right? It's just saying, is the first thing similar to the second thing? Okay. And in fact, you can put this in a transformer. Transformers have attention heads, as I'm sure you all know. Those attention heads are operating over queries, keys, and values, right? So it learns a set of queries to query its data, which is basically a humongous context window, which is basically a hack for an episodic memory. That's the reason they're having to make them bigger and bigger, so they can take kind of more and more context and achieve essentially what what the brain has in the form of episodic memory and what production system models have in terms of working memory, right? And it operates sort of by querying, taking a query and then using that to match to a key that gets a value, and then all of that information, that whole vector, is passed through to the next step. So it can all commingle. So it's a lot like the neural Turing machine, right? It doesn't have this bottleneck. But if you simply isolate the values that are being retrieved from the keys and queries, so you do a key query match, and then you simply retrieve a value that's associated with the vector that the query key match found, you basically have the relational bottleneck. And so we've built transformers called abstractors. This is work done by a colleague of mine, John Lafferty at Yale, with a student of his, Ani Altaba, and show that it has all the properties of the ESBN. And because now you can stack them, right, you can actually do more complicated things. And so we've shown that this works not only in visual reasoning tests of the sort that I've showed you here, but in sorting tests. Here it was a transformer. So Q-sort can be learned by this thing in again, about 3 orders of magnitude more efficiently than a standard transformer, and sequence learning. And here we've begun to map this into, or use it to simulate tasks that we can have people do. And it shows many of the properties that people exhibit. For example, advantages of block versus interleaved training. One of the curricular points that I sort of alluded to at the beginning that I think is central to how these things work. So, okay, so that sort of shows you how it works, or that it works and how it works. And I want just to take a quick moment here. Yeah, so I should be done in at least a couple, 5 minutes. Is that okay, John, if I take another 5 minutes? Sorry.
Yes.
Okay, great, thanks. The question now is, are transformers doing anything like this, or are they really just memorizing stuff? And they're certainly memorizing stuff, and it may be that some are only memorizing, but we've looked in ones to which we have access to the inner representations, and asked, have they implemented anything like this relational cross-attention or abstractor-like relational bottleneck mechanism? And to do that, we picked a simple set of sequence tasks, the sort that I've been discussing all along, ABA or ABB, and we got a bunch of LLMs, not the biggest ones, but ones that were, on the one hand, capable of performing this task with basically one-shot learning, where you or two-shot learning. You give it 2 examples of the sequence like this, and then you ask it to solve it on the third, all quote-unquote in-context learning. One of my least liked terms. It's reinventing the idea of simply activation-based processing, but so be it. And so we picked models that could solve this task in 2-shot in-context learning, but that had open architectures that we could go and probe the actual representations. And I don't have time to go into all the details about exactly how we looked, but I'll just give you a quick sense of it. First, we postulated the architecture in a transformer would look something like this. There would be a first level of heads, of attention heads, that were doing the symbolic abstraction, pretty much exactly as I showed you in the ESBN model, where it sees a set of tokens, and it simply puts the symbol A down for the first, B down for the second, and then it retrieves based on the first and the second, or one that isn't like it, whether it's one of these 2 symbols or something different. Right? So this is exactly just rotated the ESBN architecture. And then another layer that actually learns based on the symbolic representations to perform the ABA task or ABB task. And then finally a stage that dereferences the symbols back to their original token. So there are these res connections in transformers you may know about that are bypasses that would allow this to sort of map the symbol back to the original token. So this was the hypothesized architecture that we hope to find in a transformer. And we did a bunch of work to lesion these transformers using what we call causal mediation analysis, where we basically either knocked out heads one by one, or we took heads and we took the state they were in for one rule and then replaced it with the state that they should have been in for a different rule, having measured the system in that configuration, and asked if we could basically force it to perform the first rule. And if we could do that by basically TMSing, right? Electrically sort of stimulating that attention head to be in the state that represented one rule versus the other, it should respond as if it thought that that was the rule that it was performing. And we did a massive search for these to see if there were any heads like this. And we didn't find many, but we found them. So these are the symbol abstraction heads, and up is higher layers. So these are the lower layers, these are later layers. And then beyond, on average, above that were these symbolic induction heads, the ones that were actually learning the function, and then finally retrieval heads. Unless you think this is a multiple comparisons, we were dutiful in doing careful permutation analysis. All of these are statistically significant at insanely high levels, like 0.00001. Okay, so these are there. And you can go in and look at them and watch the representations as they move. How they're learned, we don't have anything to say about. But I would argue that this is evidence that symbolic abstraction heads and induction heads live in transformers, at least in some instances, and it's across all of the transformers. This is the case for all the different transformers. They vary in the specifics, obviously, but the same principles apply. Okay, so back to the ESBN architecture. You can think about this, probably you've already seen it, as a production system, right? Here's the matching mechanism. Here, states of the world, the conditions. They match, they give you an output that's going to be read as an action, rinse and repeat, right? And in fact, I've taken one model and literally taken the EM and taken productions out of a production system model and plopped them in here and have it perform exactly the same task. So this works as a production system model. Basically, you have to program this, right? Now, there is a difference. Here, in a production system model, at least as I understand it, here's where the semantics are, right? There's spreading activation among these things, and so which of these you match is determined not just by the match itself, but by which things have been prior activated, because it's the state of these that matters, it's not just the match. And so the semantics lives in here, and so you have to program all of that into it. And if I have this wrong, please forgive me, and I stand to be enlightened. But at least that's my rough understanding of how ACT-R works, which is what I'm more familiar with. I don't know all the details of SOAR. In contrast, in neural networks, all of the semantics lives here. This is asemantic. This is genuinely episodic, right? This is declarative memory, but only in the episodic sense, not the semantic sense. Semantic memory lives in here, in what I would call, well, you'll see in a second. So that's sort of the mapping to production systems. It also happens to comport beautifully with the architecture of the brain. Not looking like this, but looking like this, okay? So if you think about this as the entorhinal cortex, the portal to the hippocampus, which is where we think binding and episodic memory occurs. And then these systems as where all the semantics is in the neocortex. And all you stipulate is that posterior neocortex projects to different part of the entorhinal cortex than prefrontal cortex, or at least there's some separation between these, right? And then the binding among them occurs in here. You have an abstractor in your prefrontal cortex. And we've begun to sort of build models now that are looking at using this to make predictions of human brain activity, and we have a few provisional hits. So I promised the last thing I'll do here is to just show you how this works in backprop. How do you backprop through one of these things? So think of these two as sort of those parts of entorhinal cortex or of the data and the abstract side. And what's going to happen is every time that I get a new piece of, I write to this, I'm simply going to add weights here that are proportional to the strengths of these activities. I'm basically going to take this activity pattern and plop it into my weight matrix, okay? And we call it a modern Hopfield network because that's essentially what a Hopfield network does, okay? And it's recurrent in the sense that I'm going to plop the same weights. I'm going to plop these weights here and plop these weights here, and then I'm going to use this for retrieval. So it's as if this whole thing is a Hopfield network where I get to, I guess I should have said a Hopfield network in the context of its use to model hippocampus, where it's assumed that weights are formed by rapid synaptic plasticity, sort of single shot or 2 or 3 shots. So here I'm rapidly programming these weights by simply plopping these activity patterns down into those weights. That's what LTP does, right? And I'm doing it for this side here and this side here. And then these are connected through the hippocampus. These two are bound. So this might be a unit that's sort of a conjunctive encoding of this representation. And this one is a conjunctive coding of this representation. And then these are then bound. And so now I can just keep going about doing this. And as long as I have enough units here, each of which serves as sort of a different entry, then I can encode my entries on my Turing tape. Hippocampus in this view is sort of the Turing tape. Okay? And now when I go to retrieve, I place the pattern of activity here. And now I ask, what is this best match? Well, these weights are going to give me the natural dot product, right? That's exactly what neural networks do. They take dot products of activities and weights. So this will do a dot product, which is exactly my content addressable memory retrieval operation. And it will retrieve, this will get the biggest dot product, that will activate this, and then that will, through these weights, retrieve the pattern that was originally associated with this. And because all of these weights are just, continuous values and all of these are linear or continuous nonlinear functions, I can flip it around, basically copy these weights and flip it up. It's a way of dealing with recurrence in neural networks and now train through that. So I know that was quick, but at least it gives you a sense of how it can be done. And again, I'm happy to elaborate if anybody's interested. Preserves the relational bottleneck. And now we can imagine sort of how this fits into a bigger scheme. Well, we have our encoders and decoders here. We have RNNs over here. And essentially, we've got ability to represent context that can be used for attention. The RNN is doing integration. And I think those are the critical ingredients. And so I'll just end on this summary slide saying, abstraction requires inductive biases in the architecture as well as curriculum. I haven't said much about the curriculum. The tease on that is block versus interleave turns out to be super, super important. Integration is critical. That is the formation of context representations that represent your past. It's the only way you can deal with a non-Markovian world with Markovian processes. You store representations of the past in the form of your knowledge, presumably somehow integrated. You can do that through time averaging, which is lossy. That's the way it's typically done with LSTMs. You can do it with sort of windowed integration. This is essentially what transformers learn to do, or you can do it with episodic memory, which is essentially lossless insofar as you have enough space to encode everything. And then you need attention. You do need attention, just not just attention. And attention is simply the use of context representations that have been learned with these biases to do selections of mappings or the shaping of statistical structure in more sort of continuous higher dimensional spaces. And as I said, I could do a deeper dive on this last part, but since I'm out of time, I will just skip to the acknowledgements. These are all the people who did the hard work and gave me the privilege of sort of representing it. Thank you.
In fact, that was fabulous. Thank you so much. And so what we're going to do now is I've invited 3 of my colleagues from around the country to comment or discuss or ask questions of Jonathan on it. We hadn't talked about what order they were going to go into, so I'm going to start from the bottom up. Hopefully this doesn't go against the way they see themselves. I'm going to start with Andrea Stocco. Andrea, you go first and introduce yourself, and then we'll have Christian and then Paul. Okay?
Can I just interrupt to say that I'm both honored again and frightened. These are all the luminaries that I've heard about my entire career growing up, only one of whom I've had much contact with, that being Christian. So,
well, this is I think this is thrilling to have you here for us. I think in terms of information transfer and novelty, this is just great, at least for me, to get some ideas that I had not had before. So I love it. So Andrea.
Hi. Thank you, Jonathan. That was a fantastic talk, and I'm absolutely scared to be the first to speak after you. So I'm gonna take the role of I'm gonna ask you a question that is probably the closest to neuroscience in this panel. So I really love your point about the curriculum. This is something that has been like on the back of my mind for many years now. And one of the things that I've been wondering a lot is the fact that if you look developmental, you talk about evolution, but even developmentally, the brain doesn't mature at the same paces. And even if you divide up frontal, entorhinal, and posterior parietal cortices, there is a developmental trajectory. Some parts will develop early, some parts will develop much later even. And this seems to play an important role. You don't want children to start binding at age 1, and you don't want them to start planning at age 4. You want them to develop first layers of representations that are more basic, more content-based, and then develop episodic memory, and then develop abstractions. At least this seems to be like the general rule that nature has learned. And to me, this has always been like a natural way to identify modules in an architecture by developmental times. I was wondering whether there is something to be learned about in your architecture about these distinctions, or in training.
Yeah, I mean, I agree with everything you said. John, is the format I respond, or did you want
Yes.
everybody to? Okay.
Yeah,
Um,
for 35 minutes and whatever makes sense. But we're going to start with the four of you, and then we'll open it up after that. Okay?
Okay, yeah. So, yeah, I think developmental trajectories are critical. I will be honest and say I don't have too much to say about that yet, except to share your intuitions and some work that Jay did many years ago, showing that, you can account for stage-like stages of development by the extent to which the network can exploit the structure it's learned at one level to construct new structures at the next level. And the closest we've come to that in recent work is a collaboration with another one of Jay's students, Tim Rogers, who I sort of consider like the authority on neural network models of semantic cognition with Jay, but sort of really staked that out as his space. And together we've teamed up and sort of exploit the idea that control, which is what I work on, and semantics is what he works on, are really just an artificial distinction of convenience, and that they're really just two sides of the same coin. And if you had to sort of label them differently, what you'd say is semantics is about lower order statistical structure of the features of the world, and control is about the higher order structure of those features and the semantics of the spaces that develop around those features, for example, category structure, and how that maps onto affordance, right? Which ones are useful for which kinds of actions, right? I think about an elephant differently if I want to ride it than if I want to get away from it. Right? And so if you then sort of train up a system that has a layered-like structure, but with a bit more indirection to the point that's supposed to be responsible for modulating the lower order structure in the service of action, you get sort of this natural progression of learning. And there's one paper that we just had published in Psych Review, and it's called the Semantics, an Integrated Model of Semantics and Control, the ISC model, okay? And that makes the sort of as close as we get to the developmental point. I mean, it's super crude, it's simpler soft, but I think it gets the principle across. But I think as important and I think the evolution has figured that out. Then, myelination of the prefrontal cortex happens much later than myelination of posterior structures, possibly for that very reason. You don't want to sort of commit to structure at higher levels, right, until you've got the structure on which that needs to supervene at lower levels. And so this model sort of doesn't have any myelination processes, but it sort of shows that kind of trajectory. What we learned from that model, though, or what that model doesn't explain, is how you infer the right context in which you're going to need, the context you're going to need to operate. Like, how do I infer that this is the moment where I need to run away from an elephant as opposed to step on top of it? Well, that seems sort of an obvious question. It's coming at me, I run away from it. But if it's just standing there and I want to think, well, what am I going to do? I need to evoke a context. And how do I know which is the right one, right? And so in these models, including all the predecessors and all the ones that Jay did and all the one and Tim and the Rumelhart network from which all of these originally emanated, if any of you are familiar with this, the Rumelhart semantic network, the context is presupposed. The designer picked what relevant context might be useful, and then put those one hot inputs along with features of the world, and then it was trained to sort of get the right context information based on, but it didn't do context inference. And so we, in the second line of work, which addresses, I'm mentioning this because it has to do with curriculum. We simply allow that the context had to be inferred, not by pre-specifying it, but based on the prior stimuli. So we simply took a model that was exactly like the semantic networks, but we added one extra layer that integrated the last n stimuli that it had seen. And this was square wave integration. That's why I had that on my slide where it's windowed, right? So it would take the last 3 or 5 or 10 or whatever representations, very much like in context learning in a transformer, and it would simply sum them. And it would take the sum of those representations and use that as the attention signal, as the context vector, okay? And when you train a network up like that from scratch, not only does it learn context representations, but it learns to invoke them based on the stimuli that it's just seen. And that translates into this idea that when you're learning about something, the world has temporal autocorrelation that gives you that block-like structure. So when I go to the zoo, I care about the sounds and the shapes of animals, maybe less than their color because they're all sort of gray and brown. And then I go home to my coloring book and I'm given a whole Crayola set of 57 colors and I want every animal to look different. I care about the colors less than the shapes and the sounds, right? And so I'm doing a lot of drawing and coloring about colors, and that's all summing up and creating a context vector. And that gives you maybe an intuition for why we think blocked versus interleaved. If you randomly interleaved, you'd never get the categorical structure that makes things similar along one dimension at the zoo and a different dimension in your coloring book, right? It's all still the same stuff. And when you build a model like that, you get all these things that I mentioned at the beginning of the talk. You get things like asymmetry of similarity judgments, triangle inequality, which are all context effects for free. It comes out of the training of the model. Nothing was the only thumb we put on it was this architectural bias that we set the context layer up above the initial feature encoding layer, and then we blocked the structure of the curriculum. And then that context layer was integrating over that block. That integral is essentially a soft form of relational bottleneck. It's data lossy, right? When you add up 10 representations, you don't know, you could have added 10 things in 10 different ways to get the same number 10, right? And so the integration is like a soft relational bottleneck, and it learns the right abstractions over category structure that are useful for making the right inferences in different settings. So that I know is just a promissory note, but that part of the curriculum we're all over right now. This is maybe the most interesting line of research I think in the lab is trying to understand what are the temporal dynamics. It aligns, I'll say one last thing. It aligns with empirical data about how kids learn from Linda Smith. I don't know if you know her work about burstiness.
Yeah.
Yeah. And the burstiness is exactly what we didn't know about that when we did this. And when we heard about that, we went, oh my God. And one of the things we want to do is get the exact functional form of the burstiness that she measures empirically and make that the window rather than just this hard-coded, sort of discrete window.
Yeah, the burstiness is exactly what I was thinking about when you were describing this machine. This is like wonderful. Thank you.
That's great. Christian?
I have a question and a meta question. I guess I'll ask the question first. So you mentioned the relational bottleneck prominently. Are there any other bottlenecks that potentially would be of interest? And for example, I think here of the fact that various cognitive architectures discovered sort of in different ways and at different times that grain scale matter. And so, for example, in Akdar, we broke down the original scale of the architecture into sort of what you call the atomic level of a simpler scale. And that gave us a lot of nice properties. And I think so, to some extent, with their commitment to the 50 millisecond cycle time, discovered that in different ways. And that would be an example of a sort of a different general lesson that has been learned. And I don't know that it's quite right to think of it in terms of a bottleneck, but in terms of sort of a way of scaling and organizing computation. Can you think of other ones that are fundamental, or do you think that the relational bottleneck is just the one fundamental one?
No, I would not be so presumptuous to say it's the only fundamental one. I would say it's a fundamental one that needs to be there for certain kinds of efficiency of abstraction. I presented it in a rather sort of cartooned form and an extreme form as a firewall, but then I pointed out that there's ways that you can get softer versions. So integration, there's data loss, that's a bias towards abstraction. But some of the data are preserved, right? If I integrate all colors, I'll get a different mean representation than if I integrate all shapes, for example, right? And so that's a data sensitive form of relational bottleneck because the colors are all related to each other in ways that shapes are not, and vice versa. In the broader sense, there is this notion, if you're familiar with it, of the information bottleneck in information theory, that simply says, you want to compress as much as possible. It's really just a variant of rate distortion theory that says, you want to compress your representations as much as possible. And that aligns really nicely with the idea that compression, if it's done right, is a form of can be a form of generalization. And I think we're just sort of re-expressing that idea. So if you're familiar with some of the work by like Chris Sims and others, and there are other lines of work like this that show you can sort of retrieve Shepard's universal law of generalization from applications of the information bottleneck. And this, you can think of this as sort of one example of that. So at that level, I would say it's a pretty broad principle. And I don't know, Christian, whether all the examples you gave would fit under that, but I would offer it as a working hypothesis that they might. So the specific forms of integration, the data, the structure of, what's going to be most useful, I mean, that is up for grabs. So, the visual system seems to like, linear transformations and rotations as a basis set. And so genes have learned that that's a good bottleneck. The ear seemed to think Fourier descriptors were better. And so the tympanic membrane learned that bottleneck. Those are things that are learned over evolution. Similar things may apply in the space of online, of learning, the agents learning. And I think there the devil is in the details, but they all sort of had this flavor of being a form of compression that's structured in particular ways, right? So I gave you one example of how that can happen.
Great, no, that's great. So my meta question, we're 50 years into the cognitive architecture program, and so John Paul, Andrea, and I have tried to sort of recognize and condense and formalize what's been learned, and part of the intention of that was to reach out to other communities, neuroscience, AI, robotics, to try and express the lesson that have been learned. And we've tried. I don't know that we've been terribly successful. And do you think that there is value in what has been learned in the program of research of cognitive architectures for the kind of efforts that you're doing? And if so, what's the best way to try and extract and communicate that value?
I mean, I have two really strong responses. Absolutely of value. Don't give up. Keep doing it, please. You guys have been an inspiration for me anyway, and I know some of my colleagues, and certainly the junior ones, as I expose them to that space of work. On the other hand, if you know what's good for your mental health, you'll stop right now. Because machine learning people who make the money, live in industry, and are basically ruling the world right now, don't give one hoot about principles or science. They just want to make it work. And no matter how much you talk to them about principles, unless you figured out how to get another 0.1% over the latest benchmark, right, on how to build a rocket. I mean, I see you guys have, not surprisingly, the same experience as us. When we submit papers to NeurIPS, it's just unbelievable the reviews we get. And so, I, for one, am going to keep beating my head against the wall. Oh, and I will say, by the way, as you probably also know, that very little of anything that they're doing wasn't anticipated and discovered 30 years ago, right? On the connection side, no less all the things that you guys have discovered, right? And so if they're not even willing to listen to us on the connection side and say, look, we know something about episodic memory and how, right? What's the hope? I don't know. But I don't think I think you can't stop trying. And my hope is that with us training our students to talk to each other, and interact. And I hear that happening from your community, again, through hearing John's talks and going to ONR meetings that we go to together and hearing all the people that are trying to reach out, and us doing the same. Maybe we'll build a stronger integrated cognitive science, cognitive neuroscience, I don't know what to call it, but principled science of cognition and computation that at some point they'll start realizing is useful. Can I just say one last thing? The place where I see this, where they're going to hit the wall, and if I'm trying to be strategic and think, where can we set ourselves up to have been able to say in an active way, I told you so, where they'll hear it, right, is in compilation slash automatization. So all of their agents, they decide what should be done efficiently and what shouldn't, what they're going to train. But autonomous agents, as you well know, through the process of compilation, and as I've always been interested in through the process of automatization, can know when to do that. I decide whether to touch type, to continue to hunt and peck or learn to touch type, right? I decide that. There's an intertemporal choice between the time and effort spent doing this versus the time and effort spent learning to do this. And if we could formalize that and come to some sort of unified understanding about how that decision is made, informed by the way it's going to play out in a neural network architecture, which I think we understand quite well now, and all of the work that you guys have done in facing that, in every architecture you build, what are you going to compile? How is it going to compile? What's going to be going through working memory? What's going to be directly sort of, learned as a condensed production? I think we could get ahead of them because they're not thinking about that at all. But once they have to start putting all of these LLMs on edge chips and sending them to space where they don't have access to the mothership, they're going to start realizing that they need to know how to do that, right? They can't just, call up Google Central and find out what the next state of the LLM is, right? They're going to have to put it on something small, and so it's going to have to make these trade-off decisions. So I think that's one place that we could look to developing principles and maybe even showing, ideally we show some successes that they need to pay attention to.
Yeah, no, I think that's exactly right. So I'll pass it on to Paul to give time for everyone.
Yeah, sometimes somebody should ask the question he's passionate about, but Paul, it's up to you.
Okay. Hi. Yeah, I was fascinated by your talk, and I have to admit I cheated some in preparing for this panel by reading some of your papers. And that inspired me in various ways. One of them was a follow-up on some of what Christian was talking about, having to do with what's called the common model of cognition. I don't know if you've had a chance to look at that.
I have briefly, not as much as I feel like I should.
Okay. In reading your papers, I came across at least three of what I consider to be challenges to the way we think about the common model. And I want to focus on one, but the three are whether working memory is actually a memory, the relationship between procedural and semantic memory, and the one I want to focus on, which is the relationship between automatic and controlled processing. Now, in some sense, your talk touched on all three, but it didn't really focus on those questions. But I want to focus on the last one, which showed up in one of your later slides when you mapped it onto the brain and you showed the abstract and the task-specific portions of the model. And if I understand right from one of the papers I read by you, you're proposing that as the means for automatization, that essentially the controlled processing involves abstract, or I think what you referred to there as shared representations, and the automatized processing were these task-specific representations. In contrast, in the kinds of architectures we've worked on, this goes back all the way to my thesis in '83, but in the common model, we talked about essentially procedural composition. So we go from deliberate, Christian mentioned the cognitive cycle. So a process that takes many cognitive cycles to the compilation of that process to where, say, a single rule can yield the same result. And that's generally the common model of the transition from controlled to automatic. If I understand your proposal, it's a shift from these abstract shared representations that require seriality to task-specific representations that can go on in parallel. Now, one could think of those as being compatible as alternative stories. I was wondering if you had a sense yourself as to how you think about that. Are these alternatives that are incompatible, or is there a way you can view them as two sides of the same coin?
Completely the latter. Modulo the details, right? And that may turn out to be important. I'm sure it will. But in the sort of broader way of thinking about it, I think they're the same point. And in fact, I took inspiration from the stuff that you guys have done and how you think about, composition or compilation in thinking about what might be going on in a neural network. To be fair, most of the work that we've done on that is in what I'll call the spatial domain rather than the temporal domain. And by that, I mean semantic space, not physical space. And the idea there is that when you first learn a task, you want to draw upon representations you already have. And the more generally useful they are, the more you can draw on them and the more risk you are of drawing on them at the same time. That's the idea of a shared representation, right? And then eventually, if you need to do that mapping a lot and you don't want to risk interference of that, that representation being used in other mappings at the same time, you sort of, pinocytose off a new representation that's dedicated to that mapping. And so when I say spatial, I mean exactly that. You start with low dimensional representations for things like colors and words for the Stroop task, right? And then if it turns out that you want to use the color representation at the same time as the word representation, but the word representation, you don't want it to interfere with what you're going to say about the color, you develop a new dedicated orthographic representation that's specifically, let's say, for pointing in a direction that the word tells you, as opposed to sort of reading it out loud. Right? And I'm sort of summarizing some work that we've done that maybe you've seen. So that's in the spatial domain. That's sort of the hidden layer. Like, do you have these low dimensional, we used to call them minimal basis set, but now we're going to call them compositional representations shared that are useful for mapping lots of different things, but not at once, versus dedicated ones, right? So, and that story I think is rich. I mean, there's a paper that remains to be published, but it's available in archive form that's 200 pages and covers every single phenomenon we could think of in the task, in this flat mapping task space, right? Task switching experiments, the psychological refractory periods, similarity judges, all of them that don't involve critically any sequences. Now, in in SOAR, in production, you're interested in sequences. And the compilation you talk about often is in the multiple steps. And so I think you just rotate space into time and you get the same problem, though the specifics may be different in terms of the tools you need to do it. But it's still the same idea. When you're doing multiple steps, why are you doing that? Well, because each of these is compositional. It's useful in lots of different ways, and you have a toolbox, a basis set in which to use them, and they're beautifully compositional, not only in terms of different purposes, but maybe even in the order in which they can be applied, right? Maybe there's some syntax, there's some constraints, but they're exactly the same character as these low dimensional representations we talk about as being shared representations in multitasking space.
Right. They're both notions of specialization as being the focus of automatization. The one seems to focus on specializing the representation, and the other on specializing the processing. I'm wondering if there's a joint story that could be told that sort of combines those two in some interesting way. Did we lose Jonathan?
So I and that's unfair. And I think I sort of allowed that by saying the devil may be in the details for how you treat time differently than space. That has to do with integration, right? But I think in the end, it is about the specialization of the representations. Yes, I would stake a strong commitment to that. That when you're doing it sequentially, you're using different representations. And at some point you realize that the first one you want is not the one that's sort of the entry of the in the sequence, but has exactly the mapping you need to get to the end. You've dedicated, so, if I see A, B, C, D, A, B, C, D, A, B, C, D, eventually I don't bother with the B and the C. I see A and I think D. Okay. And there's a representation, a dedicated representation that A evokes that gives me a mapping to D, as opposed to B, which then can get me to C, which then gets me to D.
So maybe the way to think about it is, so in the original steps, you have very general rules that have maybe a small number of conditions to each. In the compiled thing, you tend to have these very long sets of conditions.
That's the representation.
Essentially is a specialized representation.
That's exactly right. The articulation of the condition is exactly what's in that episodic, right? That's what you're mapping that you're going to retrieve. That's exactly right.
Okay, thank you. One other, it's more of a clarification question from early part of your talk. When you talk about the ABC and those three-part problems, and you go through one problem and you get A, B, and C for the three different shapes, and then you go to the second problem or the third, whichever is the test one, and somehow you know that the first one is still A. I wasn't quite sure how that happened, because it seems to be the focus of the abstraction.
Totally. The key is that the abstract side learns two things. It learns that 1, 2, and 3 form a set, and it always has to satisfy itself by having in memory all three of those, okay? And that it's going to lay down those symbols that it's learned always in exactly the same order, the same representations in the same order, 1, 2, 3, or ABC as I had it there.
Okay, so it learns all of that.
And on the abstract side, that's all it learns. That's all it can learn. And it's the timing of the task, which of course is, you know, central to how it's performed, that you give first one stimulus, then a second, and then a third. So those ABCs perform exactly their role. Those are the roles. And whatever you put in are the fillers. It doesn't matter because they happen in that order. And once you have literally a pointer to each of those, 3 different pointers, you could call it a pointer too, right? Now it's just a matter of when you see one of the things, you retrieve that one of the pointers. When you see the next one, you retrieve whatever the pointer is that was associated with that, and you're left with the third pointer. And those pointers are just the ABCs. And so now it just doesn't matter what the data is, because it's learned the abstract rule, and you have this variable binding mechanism. It's literally a variable binding mechanism, right? The variables are ABC, and the data, the fillers are, you know, whatever you happen to put in the order you put them in the problem. Does that make sense?
Thank you. Yeah.
Thank you, Paul. I'm going to go back to Andreas. Did you have any follow-up question?
Yes,
Besides that,
I do. I do. And it's going to be quick, and I'm going to riff off Paul's question. And that was also my other backup question was about the fact that in this newer architecture, that there is a hole, and of course, like my personal training bias, let me see like that immediately, like, because my favorite part of the brain is the basal ganglia. And you talk about procedural knowledge, but you have production rules, but you were putting that in the hippocampus, and it occurred to me that there are 2 ways to think of binding, and one is like directional, like you have a key and you read a value, and this leads to temporal dynamics, and the other is like pure superposition, which is another way to think about binding in the hippocampus. And those seems to be 2 different uses of binding, and also 2 different structures in the brain.
So I apologize for not having been more careful about that. The RNN is the basal ganglia, or contraction.
Okay.
Okay. There are loops. Randy O'Reilly, a close colleague of mine, has spent his entire career building out that idea. They're subject to exactly the kinds of, in fact, we proposed LSTMs as a model of that well before they were popular in machine learning. Hochreiter and Schmidhuber published their first paper, and literally we saw that paper and said, that's the basal ganglia PFC loop. And it's a gating mechanism. The basal ganglia gates what one part of the cortex wants to get into another, right? The prefrontal cortex acts to maintain at least some persistence and as well as integration. And so yeah, I should have labeled it. I'm sorry, but that's where that is. And you're right. That's the production part of the system.
Yeah. All right. Perfect. Thank you.
Christian, you have a small point or a question to follow up?
All right, John, are you asking if I have a follow-up question?
Sure.
Actually not.
Okay, great. Christian, could I ask the people on the Zoom to raise your hand if you want to ask a question, and I'll just let Christian fill in the blanks for a few minutes. Christian, you have anything?
Oh, sure. No, that sounds, fill in the blank sounds like a really important role. So to go back to the last thing that in Jonathan's answer to my question about the importance of sort of that. He talked about compilation and automatization. I thought of it as metacognition, which is something that we're discussing very much right now in the context of the common model, and something that we've in a couple of instances used cognitive architectures as metacognitive overseer of more automated neural net type system, which seems to be a natural sort of separation of specialization there, and then really the best way of leveraging the generality of cognitive architectures. Do you think of that kind of thing as a separate system? Do you think as something that should ultimately be integrated into the sort of the lower level system itself?
So I'll swap out the light bulb joke for a different metaphor. I am a connectionist in the following sense: it's turtles all the way up. And so I think that it's true. There's a level of analysis. I made a point of pointing that out, and I know that you agree, of when you decide or how you decide what's worth automatizing and what's not, right? But I think that we can invoke the same kinds of learning mechanisms one layer up. Now, at some point, you have a halting problem, right? I mean, you can't go forever, right? Horowitz and Russell noted this in terms of the cost of computation analyses they did many years ago. And, obviously the brain faces that. So how many layers up you get to go, I don't know, but we have some examples where you can invoke, for example, reinforcement learning mechanisms to make that choice. So there's a paper, unfortunately not published, but it's also available in arXiv, a deep learning neural network in the multitasking space. It's, again, not sequence learning. It's about whether it's going to learn separated or shared representations for simple IO mappings, right? But it's, I think, in my response to Paul, I think it's a similar principle, where an RL mechanism can learn when it's worth doing that. And that was based on a simpler sort of Bayesian analysis, where you can sort of write this down in the simplest, most abstract form as an intertemporal choice. That is the cost of serialization against the cost of training. And if the system has some way of estimating its learning rate, and you put a cost on serialization, that is the time it takes to do something, you can find out, what the optimal thing to do is, and then you can parameterize it to learn that. And so there's a couple of papers I can point you to if you're interested in that. They're very simple models, but I think they point out how one could take this on with the same kinds of approaches and apparatus that we've taken on these other problems. So, and is it specialized? I mean, is it another layer specialized? It's different than the lower layers, but it's sort of doing the same stuff.
Thanks. Jiyu?
Hi, I'm Zil, and I'm a postdoc from UC Santa Cruz. And I really like, your talks and all your thoughts, especially on how you talk about, these the metacognitive process of these models on things like sample efficiency and their performance on pattern recognition. So my question is, I want to dig a little bit further into this metacognitive process, especially on the architectural model and their influence on the sample efficiency. So to make it very simple, do you think this sample efficiency comes from they are either trained differently or the model architecture being differently? Or do you think that humans just have, I would say better, maybe that's not a better word for that, a better way to, look into patterns, learn on these patterns, or just having overall, a metacognitive process that the neural networks or other AI models are not able to master yet?
I can't answer the last question. That's sort of where the research lies. I don't know what makes people special, either with respect to other animals or I think I have some ideas about what makes them special with regard to the current generation of large neural networks. And it is the inductive bias. So the ESBN model benefited not by curriculum. There was nothing about the curriculum. We trained it on the same curriculum that the transformer got and that all the other comparison models got. It had nothing to do with the curriculum. It was entirely the inductive bias. That said, the model that I was mentioning in response, I think it was to Andrea's question, this integrated semantics and control context inference model, does leverage curriculum to do even better. Honestly, we didn't really look at the sample efficiency because we don't know what to compare it against. I mean, we did compare it to existing transformers on its ability to perform these semantic tasks, but we didn't train those transformer models. So I don't know what the sample efficiency is there of the curriculum. But in other work where we've looked explicitly at blocked versus interleaved training, and there it was in sequence learning. So there actually, now that I think about it, I should have mentioned this. There is one example where we have these models doing sequential performance tasks, learning sort of finite state grammars, if you will. And we didn't do any work on compilation there, but that's a place we could look. In any event, where we look, the model does benefit in terms of its efficiency based on the curriculum. But that wasn't really very richly explored, so I don't want to say that with too much confidence. But I have a very strong intuition that it'll be the interaction between the two, right? You learn math better with a good teacher than a bad teacher. Maybe that's a soft statement, but I think there's some truth to it.
All right, our final questions for Brian.
Hi, and thanks for the talk. That was wonderful and fascinating to listen to. I just had a really quick question. If one wanted to like download and try out some of the models you talked about in the various iterations, do you have a recommendation of like where to start as far as like easiest to start learning and diving into, requiring least amount of like expertise and how to get it to function well, that sort of a thing?
Great. I'm really glad to hear you're interested. You know, the most responsible advice I could give you is PyTorch, and then I can point you to some implementations of our models. That said, as Christian knows, and I'm a little bit embarrassed to admit, I've been working for many years on basically an API. Didn't start as one for PyTorch, but it can be thought of that way right now. It's called Sinulink. And it's in Python, but it's an attempt to try and distill away all the under the hood, machinery and magic of, atom optimizers and, all of the crazy stuff of neural networks, and just give you tools that are pretty much well enough formed to do interesting stuff with in a way that you'd recognize it. So I have an episodic memory mechanism, I have an RNN, and then other standard stuff like decision-making modules. It's sort of like a plug and play Lego environment where you can put together models. And if you're interested, I would love nothing more than for people to be trying it. We've never advertised it or promulgated it because I don't want to do that until it's totally rock solid and I feel like I have enough models that are useful. And so that's why it's taken so long. But I think it's getting close now. And some of these models, we just sort of crossed threshold in getting them implemented. So the ESBN model is now implemented, and there's a few others that I've referred to that are implemented. And it also has the virtue of having built-in optimization, not backprop, but like standard grid search for hyperparameterization. Those are tools that are built into the environment. So it does make it a little bit easier to get models not just built, but to work. And so if you're interested, just reach out and I'd be happy to point you, and any time you're willing to spend playing around with it would be tremendously appreciated, especially if it comes with feedback.
Awesome. Thank you so much.
This was fabulous. I just want to thank Jonathan, Andrea, Christian, and Paul. This really was informative, and I think a lot of us learned new things, and I think it will affect us in our research. So I can't ask for anything more, Jonathan. So thank you so much.
Thank you.
Uh,
And I look forward to continuing the conversation.
and Ahoy, your comments about publication and transfer of information, I just don't know how I think there is a community of people that are like-minded, and that we have to find a way, and not just at ONR program reviews, to get them together, and there should be more crosstalk across these levels and across the people doing this. So
Maybe CogSci. Somebody, it'd be great to have a CogSci symposium on this.
Well, there's also ICCM, but maybe that has too much of a reputation of symbolic and not. I don't know.